Appendix XII of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix XII. The Three-Wire System. This invention is covered by United States Patent Number 274290, issued to Edison on March 20th, 1883. The object of the invention was to provide for increased economy in the quantity of copper employed for the main conductors in electric light and power installations of considerable extent, at the same time preserving separate and independent control of each lamp, motor, or other translating device upon any one of the various distribution circuits. Immediately prior to this invention, the highest state of the art of electrical distribution was represented by Edison's feeder system, which has already been described as a straight parallel or multiple arc system, wherein economy of copper was obtained by using separate sets of conductors, minus load, feeding current at standard potential or electrical pressure to the mains at centers of distribution. It should be borne in mind that the incandescent lamp, which was accepted at the time as a standard, and has so remained to the present day, was a lamp of 110 volts or thereabouts. In using the word standard, therefore, it is intended that the same shall apply to lamps of about that voltage, as well as to electrical circuits of the approximate potential to operate them. Briefly stated, the principle involved in the three-wire system is to provide main circuits of double the standard potential, so as to operate standard lamps or other translating devices in multiple series of 2 to each series, and for the purpose of securing independent, individual control of each unit, to divide each main circuit into any desired number of derived circuits of standard potential, properly balanced, by means of a central compensating conductor which would be normally neutral, but designed to carry any minor excess of current that might flow by reason of any temporary unbalancing of either side of the main circuit. Reference to the following diagrams will elucidate this principle more clearly than words alone can do. For the purpose of increased lucidity, we will first show a plain multiple series system. In this diagram, G1s and G2s represent two generators, each producing current at a potential of 110 volts. By connecting them in series, this potential is doubled, thus providing a main circuit, P and N, of 220 volts. The figures marked L represent 8 lamps of 110 volts each, in multiple series of 2 in 4 derived circuits. The arrows indicate the flow of current. By this means each pair of lamps takes, together, only the same quantity or volume of current required by a single lamp in a single multiple arc system, and as the cross-section of a conductor depends upon the quantity of current carried, such an arrangement as the above would allow the use of conductors of only 1/4 the cross-section that would otherwise be required. From the standpoint of economy of investment, such an arrangement would be highly desirable, but considered commercially it is impractical, because the principle of independent control of each unit would be lost, as the turning out of a lamp in any series would mean the extinguishment of its companion also. By referring to the diagram, it will be seen that each series of 2 forms one continuous path between the main conductors, and if this path be broken at any one point, current will immediately cease to flow in that particular series. Edison, by his invention of the three-wire system, overcame this difficulty entirely, and at the same time conserved approximately the saving of copper, as will be apparent from the following illustration of that system in its simplest form. The reference figures are similar to those in the preceding diagram, and all conditions are also alike, except that a central compensating or balancing conductor, Pn, is here introduced. This is technically termed the neutral wire, and in the discharge of its functions lies the solution of the problem of economical distribution. Theoretically, a 3-wire installation is evenly balanced by wiring for an equal number of lamps on both sides. If all these lamps were always lighted, burned, and extinguished simultaneously, the central conductor would in fact remain neutral, as there would be no current passing through it, except from lamp to lamp. In practice, however, no such perfect conditions can obtain, hence the necessity of the provision for balancing in order to maintain the principle of independent control of each unit. It will be apparent that the arrangement shown in Fig. 2 comprises practically two circuits combined in one system, in which the central conductor, Pn, in case of emergency, serves in two capacities, namely as negative to generator, G1s, or as a positive to generator, G2s, although normally neutral. There are two sides to the system, the positive side being represented by the conductors P and Pn, and the negative side by the conductors Pn and N. Each side, if considered separately, has a potential of about 110 volts, yet the potential of the two outside conductors P and N is 220 volts. The lamps are 110 volts. In practical use, the operation of the system is as follows. If all the lamps were lighted, the current would flow along P and through each pair of lamps to N, and so back to the source of energy. In this case the balance is preserved and the central wire remains neutral, as no return current flows through it to the source of energy. But let us suppose that one lamp on the positive side is extinguished. None of the other lamps is affected thereby, but the system is immediately thrown out of balance. And on the positive side there is an excess of current to this extent which flows along or through the central conductor and returns to the generator, the central conductor thus becoming the negative of that side of the system for the time being. If the lamp extinguished had been one of those on the negative side of the system, results of a similar nature would obtain, except that the central conductor would for the time being become the positive of that side, and the excess of current would flow through the negative N back to the source of energy. Thus it will be seen that a 3-wire system, considered as a whole, is elastic, in that it may operate as 1 when in balance and as 2 when unbalanced, but in either event giving independent control of each unit. For simplicity of illustration, a limited number of circuits, shown in Fig. 2, has been employed. In practice, however, where great numbers of lamps are in use, as for instance in New York City, where about 7,000,000 lamps are operated from various central stations, there is constantly occurring more or less change in the balance of many circuits extending over considerable distances, but of course there is a net result which is always on one side of the system or the other for the time being, and this is met by proper adjustment at the opposite generator in the station. In order to make the explanation complete, there is presented another diagram showing a 3-wire system unbalanced. The reference figures are used as before, but in this case the vertical lines represent branches taken from the main conductors into buildings or other spaces to be lighted, and the loops between these branch wires represent lamps in operation. It will be seen from this sketch that there are 10 lamps on the positive side and 12 on the negative. Hence the net result is an excess of current equal to that required by 2 lamps flowing through the central or compensating conductor, which is now acting as positive to generator G2s. The arrows show the assumed direction of flow of current throughout the system, and the small figures at the arrow heads the volume of that current expressed in the number of lamps which it supplies. The commercial value of this invention may be appreciated from the fact that the application of its principles there is effected a savings of 62.5% of the amount of copper over that which would be required for conductors in any previously devised 2-wire system carrying the same load. This arises from the fact that by the doubling of potential the two outside mains are reduced to 1/4 the cross section otherwise necessary. A saving of 75% would thus be assured, but the addition of a third or compensating conductor of the same cross section as one of the outside mains reduces the total saving to 62.5%. The 3-wire system is in universal use throughout the world at the present day. End of Appendix 12.